All right, so last time we looked at some classes and stuff, right? We had that C++ class example, this guy. So we looked at our header files, how this looks a lot like what we would have seen in Java, but without the implementation. So these two files kind of put together, the header file and the C++ file, merged together, accomplish what we typically have seen in a class file in Java. So nothing earth-shatteringly new, just take some practice to get the little nuances of the syntax down. So what we're going to look at today is structs, which are kind of a interesting twist. They're like dictionaries in Python. They're the precursor to classes from the C programming language. So they kind of predated classes and maybe are the driving force between C and then C++, why we added object-oriented coding to that. But we are going to see an interesting difference between structs and dictionaries from Python. And that's going to give us a little bit more practice with pointers and things like that. All right, so in the meantime, I already have an assignment up, which is just a kind of a short paper. Remember, we don't have class on Monday because of, was that Labor Day? So the next time we'll meet is on Wednesday. So it's a 2-page paper comparing Java, C, and C++. So it should kind of take you from where you were to where we're going and cover what we're talking about today. And we should be starting our programming here in full effect here pretty quickly. And that's already up on Blackboard. All right, so before we go on, any questions about the whole header file, dealy flippy stuff? We're kind of seeing where that's coming from. All right, so let's look at structs. So we're going to kind of create something similar to what we did last class with our class that was for a person. And here, I'll steal this as my starting point, then just update the. So I'll go into Maincpp. And this is where I'm creating instances of my my person thing. But what I'm going to do up top is I'm going to go ahead and invent my own data type. We're going to call this guy a person struct, just to keep them clearly defined, since I also already have a person class in here. All right, so what I'm doing here is I am creating my own data type. I'm saying that I'm going to have something of type person struct that is going to hold 3 pieces of information. And I think we looked at strings last time, right? Yeah, I looked at this string class. So actually, why don't we go ahead and we'll use, rather than using old style strings, which are char pointers, I'll use our new style string. All right. We did talk about old style versus new style strings last time. Or did I just assume? Let's just look at this real quick. What did I do in here? Those were strings to begin with. All right, let's just talk about that real quick, and then we'll jump into structs. So I'll just pause that up there for well, here, I'll just get rid of it for a moment. All right, so if I create a char pointer called S, and I set this guy equal to hello world, something like that, I'm creating a, this is a string. We would call this guy a string, but in reality, what we just generated is an array of characters. Okay, that's what a char pointer is. Let me show this to you as when we talk about arrays, these are things stored in contiguous memory, right? So memory right next to each other. So wherever this S exists, I'll go ahead and do a cout S. Let's just see what that guy does with what cout does with old style. Does it give me the address or gives me the contents? Oh, because I'm in C++, it doesn't want me to use this old style. See if I can force it by jumping to C, or is it going to scream at me about the classes? Yeah, it's screaming at me about the IO stream stuff. All right, it's fine. I'll just explain it like this. What this effectively is doing, if I were writing this in C, in fact, actually, let's just create a new project. That'll let us do it. This is just a standard thing. I'll switch it over to C. I'll do char pointer S is equal to hello world. Let's make sure he's cool with that for the moment. He is. All right, so first of all, we're kind of seeing, this is really leading us into what that paper is about. The difference between C and C++ and Java, because I'm using what I've referred to as an old style string, those existed in the C programming language. Since I was in my language choice and the other one as a C++ language, it was running it through the C++ compiler. Now, C++ does support old style strings with certain compiler flags, but since I also defined classes in that other project, which are not supported by C, C does not, classes don't exist in C. That's the whole point of us talking about structs today, is structs were our predecessor to classes. This guy wasn't going to work, but we'll force the issue here. So we have a char pointer S is equal to hello world, and then I'll go ahead and I'll do this as old style output using printf instead of cout. We talked about that last time. We looked at 3 different ways of doing output. So printf is a kind of our older output function, but I would say still pretty relevant since it allows us to do formatted strings. I still use printf fairly often. Cout sometimes is great just for a quick output, just to check something, but really if I'm trying to do anything with more than a couple of embedded values, I'll use printf. All right, so we'll go ahead and we'll say, I'll say %s is the value and %p is the location. And then I'll put in a, oh, why do I keep pressing save? And then we're gonna put, see, star s is the value and s is the address. Oh, because it's treating it as. All right, so hello world is the value that's stored inside of our string. %s says treat this guy as a string. Since we're treating it as a string, and strings are collections of characters, by definition, they're a pointer type. So I don't have to specify the pointer syntax here for it because I said %s. But if I say, actually, let me do that real quick, make sure I get a value. Yep. is the location of the string, and %p is the location of variable s. This will close our thing that we said last class. And here, I'll put a couple of carriage returns in here. It'll read a little bit better. Let's see what that looks like. All right, so I've created a single variable here, s, and I set it equal to hello world. And now we're seeing 3 different values that we can get associated with s, because we're really trying to drive this point home of working with pointers. All right, so the first value, this is a placeholder for a string, %s, is something built into the language. It's an old style C string. So %s is a placeholder for a string. It knows that even though s here is a pointer type, it knows that what it contains is a pointer that needs to be dereferenced to an actual string. That's why I didn't have to do any sort of special syntax here saying the value at s. That's how I would read this. If it was any other type other than a string, I would read $s as the value that lives at the address contained inside of s. That's what $s would mean. But in this case, since C has a placeholder called %s, it knows to treat s as a address that needs to be dereferenced. So I don't need to say $s, I just say s, because s holds the address that this guy will automatically go and look up and find the string that lives there. All right, so hello world is the value that ultimately is stored in s, well, ultimately that s points to. All right, so hello world is the value that it points to. This next address, this is a memory address, and this is a different memory address. So this is kind of driving the point home we talked about last time. The second memory address here, notice here that %p is a placeholder for pointers. That's what %p stands for. All right, so this guy is s itself. Okay, so this is saying what value does s hold? S is a pointer type. Here's my variable named s. The kind of animal that lives inside of s is a char pointer. All right, so the value of s is a pointer, and that pointer is this guy. So what I have highlighted there is the location in memory where our string hello world actually lives. Okay. This last pointer here, this %p, where I'm saying the address of s, this has nothing to do with the string. This has to do with the variable, the place in memory that I have created to hold something. I have a variable called s, and that variable lives somewhere in memory. All right, so this address right here is the place in memory where s lives, where it was created and is sitting there holding another value. So at this place in memory, there lives a variable. That variable contains this value, which points to this value. Make sense? This is no different than Java. We're just seeing it. Okay, Java works in the identical way under the hood. Okay, we're just seeing it here. And Java even does more, fakes us out even more with strings, right? Because Java treats strings as primitive types. So there's like no way to get to a memory address of a string in Java. You can't even fake it and see it. You know, you have to, you're completely bypassed. All right. So questions about that? Now, what if we wanted to see individual characters of our string s? So I can say printf the char at bucket 0 is s at bucket 0. which is a character. So that's a %C placeholder. S at bucket 0. And we'll do an S at bucket 2 here is another one. S at bucket 2 is %C. All right, so %C placeholder for a char. So this is going to write something out to the screen. The char at bucket 0 is some character. Which character? Since this is the first placeholder we ran into, it'll be associated with this first thing we had here, which is bucket 0 of the character array that is S. So in old style C, the difference between a character array, a char array, and a string is nothing. We just happen to have this convenience placeholder inside the language that says, you know what, as a programmer, you're probably going to be using strings somewhat often. So we're going to go ahead and we're going to give you a special kind of placeholder that just makes your life slightly easier. You don't have to dereference it. But under the hood, it's a char array. We can say in Java that the string class is very likely written in terms of a char array, where here we can just say it is a char array. We're looking at something that is a char array. So there, the char at bucket 0 is our H for in hello world. The very first element is an H, and S at bucket 2 is a L. Bucket 0, bucket 1, bucket 2 is our L. Make sense? All right. Another interesting thing is, what if we wanted to get the length of our string? So this is kind of an interesting thing here. We can say the length of S is, now we would say the length of something is probably some kind of integer, right? So our placeholder for integers is %D for decimals. So the question is how do we get the length of effectively a character array? And we actually saw this last time. At least I think I filled it in. Did I show you command line arguments last time? Did we have an int argc, char, pointer, argv? Okay. So in Java, when we create our main method, all programs begin and end with main, right? In Java, when we create our main method, we have our public static void main string array args, that thing. So this guy right here is an array of strings. A pointer is a base address. So this is a char pointer of char pointers. This is a collection of pointers where each of those pointers points to a string. All right. That's the same thing as string array args in Java. It's an array of strings. This guy is an array of strings, just written in a scary looking way. It's an array of char pointers. So it's a char pointer. The first pointer points to the base address of the array, and then the kind of values that live at each bucket of the array is a char pointer, which points to a string. Okay, but the difference is in Java, our main method took one parameter. In C, as well as C++, it takes two parameters. The question is why? It's because in C and C++, an array cannot tell you its length. In Java, that's string array args, we could say args.length, and that tells us that, oh, there's 3 things in it, there's 5 things in it, there's 7 things in it, whatever it is. An array in Java is a more advanced critter than it is in C++. That's something you're going to see when you look at the compare and contrast C, C++, and Java. And if you go back to our picture from last class, it kind of makes sense that This dude probably has some conveniences added into it that this dude didn't. This dude probably has some conveniences added to it that this dude didn't. This guy had structs, which were almost as good as classes, but not quite. So now we introduce classes. This guy had a lot of good things, but you know what? Pointers are kind of scary and get you into trouble more often than they should. Every now and then, it's nice to be able to leverage memory, but sometimes, maybe more often than it should, it's just more trouble than it's worth. So what did Java do? It hid the syntax for pointers and just said, look, let us take care of it. We'll figure out when something should be an address versus when something should be a value. All right. So that's conveniences for us. But now we're seeing some of those, since we're going back, we're seeing some of those holes. So in C and C++, the array primitive type does not know how to advertise the number of elements that are in it. It can't do it. So that's why with main, we have two parameters. They don't have to be called argc and argv, but they do have to be an int and a char pointer. Or in C++, you could say it's a char pointer. C++, it almost looks a little bit cleaner. It's a array of, so when we see something like this, that kind of looks like it's an array thingy, right? That's an array of what? An array of this kind of thing. Char pointers, where a char pointer is a string. But I mentioned that these do not need to be called argc and argv, but that's traditionally what they're called because they stand for something specific. This is the argument count. How many arguments were there? This is the argument values. What were the arguments? And this gives us command line, the ability to pass in command line arguments, which is something that isn't very common today, right? Because most of our programs today are graphic user interface programs with buttons and things like that. But if I were to compile a program from the command line here, let's see, I have an example already that I used in 200. So here's a main method in C, and notice here that here I'll just add something here. I'll say printf number of inputs is %d, and that's going to be argc. The third input is argv at bucket 3, something like that. All right, so now I'm going to use these two values that are passed in. I'll show you kind of where they came from. Okay. Again, this is something that isn't common for us today as modern software developers. But if you are writing command line tools, which are still powerful things, you very well might use this type of thing. So now when I run this, well, so first of all, you can kind of see it through an example right here. I'm about to use the C program, the C compiler called GCC. This is the GNU C compiler, GCC. So this is a program very likely written in C. So somebody wrote this program, and in order for GCC to work, if I just type in GCC and press enter, it's going to yell at me. It's going to say, hey, you didn't give me any input files. This isn't a syntax error. This is something that was logic inside that program that said, look, I looked for the file you wanted me to compile. That is, I looked for a single input, and you didn't give me one. Because this program, GCC, requires that you give it some information on the command line inputs. So I'm going to tell it that I want to compile that program, hello200.c. So now I've given it a command line input. So I'll go ahead and run this. So I must have forgotten a curly brace somewhere. Number of inputs is right there. All right, so what that just did is it created an executable file for me, which is called a.out by default. So there's my executable. Now, if I run this right now, I'm going to get an error. It's going to say, hey, if you look at the code we had up here, if I run it and I don't pass it any command line arguments, this line right here is fine. It's going to say, oh, the argument count was, and actually the argument count will be 1 because C treats the name of the program, a.out in this case, as your very first argument, the argument at bucket 0. So my argument count would be 1. But if I tried to print out the argument at bucket 3, the third string I passed it, or really the second extra string I passed it, it's going to scream at me because if I don't pass it any extra stuff, notice it says the number of inputs was 1. That's the a.out. The third input is right here. This is what's called a buffer overrun, memory leak. I've walked off the end of argv and I started jumping into other places in memory where this thing is, some MAC memory address where a string is stored. So it didn't stop me. In Java, I would have gotten array index out of bounds, right? It would have yelled at me and said, hey, you walked off the end of this array. C and C++, arrays don't know how long they are. Yeah, you walked off of it. Here you go. This is what I found at that memory location. Because with strings, if I have a collection of char pointers, how does it work? You go to the base address. If I say I want bucket 3, and the size of a char pointer is, let's call it 32 bits. I think it's actually 48 bits in Mac OS for the size of a memory address, because that's what I'm storing there. Char pointers are memory addresses. So I will take 3 memory address size steps off of the base address of my argument values. So if I come in here, I'll just do it on this slide. So argv is going to hold some crazy address. Something like that, some hexadecimal address. All right. Which ultimately is going to point to some places in memory like this. We could say this is bucket 0, this is bucket 1, this is bucket 2. And actually, let's just assume these are simple memory addresses. I'll just say it's memory address 100. We'll keep it in human readable decimal stuff. So bucket 0 actually lives at memory address 100, like this. So we're going to say these are the memory addresses. These are the indexes. And these are the values. All right, so if argv happens to have a base address of 100, that means that the guy who lives here is a pointer to a string, a char pointer. So the size of this bucket is the perfect size for a memory address, which let's just assume if you're in a 32-bit operating system, it's a 32-bit memory address. If you're in a 64-bit operating system, it's a 64-bit memory address. Linux actually uses 48-bit memory addresses because it reserves a portion of memory addresses for the system. And you've actually already seen that in here when this memory address was much smaller than this memory address. So you've kind of seen under the hood what Linux is doing in terms of saying, look, I'll give the end user 48 bits of memory space to work with, but I'm going to keep, what is it? 16 bits. I'll keep 16 bits of memory reserved for the system to create base addresses. This is just what they decided. All right, so if we assume that, let's just keep it simple here. Let's say we're dealing with 32-bit memory addresses. That means that this is memory address 104. 32 bits is 4 bytes. This is memory address 108. So if I say argv at bucket 0, what this is really saying is go to the base address of argv, add to it 0 times size of pointer, which we just said is 4 bytes. So that's equal to 100 plus 0 times 4, which is 0, which is 100. So bucket 0 lives at memory address 100. Similarly, bucket 2 says go to the base address, add to that 2 times size of pointer, which is 100 plus 2 times 4, which is 8. So that gives us 108. Bucket 2 lives at memory address 108. So in my example that we just ran, when I said ./a.out, that's the name of my executable. That's also what will live at bucket 0 of argv by default. And then I didn't pass it anything else. I just pressed enter. That means what was in here was the string ./a.out. That's what lived there. And here, I'll just take the string part off. Let's just say that's what lived there. But that's all that was reserved for argv by this program. That means that if I try to say, go to bucket 2, that's just going to take me to memory address 108 and show me whatever's there. Whoever put it there. All we know is it wasn't us. Make sense? That's what CNC++ lets us get away with. We can make the argument that that's one of the reasons why in Java, they manage memory for us rather than give us a syntax to deal with it ourselves. Because we're allowed to just walk all over the place in memory in CNC++, whether we belong there or not, right? We just saw that it didn't keep us from walking to bucket. I mean, heck, I can go in here and I can just say, oh, what I was doing out here, right? I mean, let's just go to bucket 300. As long as that doesn't randomly take us near the end of memory. Ah, it did. So there was an amount of memory that it reserved for this program running, kind of like in a virtual machine, and we walked off the end of it. So we got a segmentation fault, which is sort of like an array index out of bounds, but it's nothing to do with our data size. It's the amount that the operating system gave to this running program to run. It's a protection mechanism to keep your programs from overwriting crazy amounts of memory. But we can circumvent it a little bit. We'll just put a smaller number in here. Maybe like bucket 8. So there's something else that lives at bucket 8. Actually, it looks like the same thing. So they must have, because I'm in the terminal, it must have pre-filled all memory with that string. something along those lines. But what's important for us is it didn't keep us from walking all over memory. All right. So argc is the number of arguments. And here, let me change this back to a 3 here so I can show you what if we do actually pass in arguments. File that again, run it, and we'll say cat, dog, elephant. So this is argument 1, 2, 3, 4. This is at bucket 0, bucket 1, bucket 2, bucket 3. 4 total elements. Bucket 3 was elephant. That's what that argc and argv are for. Similarly, that's in Java what args is for. If I was in Java, it actually does not keep track of the a.out part, the name of the program. Java would have the length of args would be 3. Bucket 0 would be cat, bucket 1 would be dog, bucket 2 would be elephant. So the exact same rationale, it allows Java to take in command line arguments. The little difference is that C and C++ get the name of the program that's being run. Java does not, doesn't automatically read it. All right, but again, that's something that modern programmers kind of rarely use. We don't write programs that take command line arguments all that commonly today, but we can, even in a more modern language like Java, which it's been around for a few minutes. Java's been around longer than most of you. But relative to C and C++, Java's a new kid. Okay. Oh, what am I doing here? But we need the 2 different parameters because this guy is not able to report to us how many buckets he has. That's why we have this. We sort of kind of, and at some point we'll run into an example of it, but we sort of kind of have a backwards way that we could determine the length of a string. All right. Let me actually show that to you. We'll come in here. All right, so before I go on, any questions about this? The difference between the pointer to where the string lives versus the address where the variable lives, the address that the variable contains versus the address where the variable lives. This is the value that lives at our string. That's the %s. The location of our string, that is the value that lives inside of our string. That's where the string lives. Hello world lives at this memory address. And my variable s lives at this memory address. 3 different pieces of information we can get from the exact same variable since we're dealing with a string type. If we were dealing with a non-string type that we didn't have to dereference, let's say we were dealing with an int, then we'd have 2 different pieces of information. Because the address itself holds the static value, the literal int, and then that variable also lives somewhere in memory, which we really don't care about. That's not something that we would regularly use in any of our programs, right? Like when you're thinking about where a programming language tries to mimic our understanding of memory, human beings remembering things, right? So when I say, what's your name? You know that somewhere up in your head, you're going and looking that up, right? You don't care what part of your brain that little mapping is. My name equals Mike. You don't care where that is. You just know it's up there somewhere. So we don't really care where that variable s, where the operating system chose to put s to hold our string. This just proves that if we really did want to know, we could. Make some sense? All right. Now, an interesting thing with chars is an interesting thing with old style strings. These guys are terminated by a special character \0. This is called the string termination character. So what becomes kind of interesting about this is that string termination character, because we know that strings do end with a \0, we could write our own function that will tell us the length of a string. As long as we know where the string starts, we can start walking the string one bucket at a time until we get to a \0. Make sense? So let's look at that by example here. I'm going to actually write it down here. Hopefully this old compiler gives us the error that I want it to give us. Otherwise, I'll force it. So we're going to write a function. So this is outside of main, but inside of our file. So it's just another function in the procedural language that we're going to call. And we're going to call this guy, we'll call it string length. And it'll take a char pointer as a parameter. All right, looks pretty similar to a Java function. Return type, name of function, parameters. Nothing crazy there. All right, so now what we want to do is we want to start walking our string from the very beginning of it, which is stored inside of S. That's the base address of our string, is the value that lives inside of S. And I want to ask, is that guy a \0? If not, add 1 to my length, keep going. So I'll say cur length starts off at a 0. Let's see if we can just do it with a single thing. So we'll say while the value that lives at, I'm going to do actual pointer math here so you can actually see what I showed you before when we well, here we'll just do it before I write that. I'll do a printf %c \n %c, and I'm going to write C at bucket 2 different ways. The first way will be a familiar way. Actually, it's S at bucket 2. That way is familiar, right? So when I say S at bucket 2, this should give me, this is bucket 0, bucket 1, bucket 2. It should give me this L. Make sense? But like we just wrote on the slide, this is a convenience syntax. This is using array syntax for walking through an array of chars. But I can say, go to the base address of S, add to it 2. And give me the value that lives there. Those 2 things will give me the same value. Oh, misspelled printf. L and L. This is called pointer math. And really, I'm not doing anything special. A pointer is a hexadecimal number. It's an address. This kind of goes back to what we talked about last semester and the semester before that, where we talked about computer all of our houses. It's like a street, a single long street with millions of houses on it. In real life, our addresses for our houses are much more complex. We have a house number, we have a street number, we have a city, state, zip, right? We have complex addresses. In computers, they're very easy. This is thing at bucket 0, bucket 1, bucket 2. That's memory address 6 zillion, blah, 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 blah. And they put them in a crazy looking hexadecimal value, which makes them look intimidating to us. Make sense? But it's really just a big number, and hexadecimal is a more compact way of representing large numbers. So when I say S right here, I'm saying take me to where this string starts in memory, and then add 2 memory size steps to it. So take me 2 places, 2 addresses later. So this guy right here will be an address. Putting the asterisk before it says, give me the value that lives at that address. That's what asterisk says. It says dereference an address and give me the thing that lives there. You want to think about this in real life? If you go to my house, given the address, when you're standing outside, you're standing at the address. When you walk through the door, now you're looking at the value at that address. All right, so star whatever would be the thing that's contained at an address. All right, this makes sense? You never have to use a syntax like this. It's just what the cool kids would do. If you look at old C programs, it would be common to see syntax like that. And it's not just randomly showing off as much as it is not treating this guy as something special. An array just happens to be stored in contiguous memory, which means that we can walk an array given its base address and an offset. This just proves that it's stored in contiguous memory rather than some mystery of, oh, whatever that syntax does. All right, so let's write our string length thing here real quick. So we'll say int count is equal to 0. We'll say while the value that lives at s plus count is not equal to a \0 count plus plus. Actually, it's entirely possible that their version of the C compiler the plus plus operator came much later. So if we want to be careful, we'll say count plus 1. In the end, we'll return count. And then up here, I'll go ahead and print out %d string length of s. The number of chars in S is that guy. All right, so I'll call string length. I'll pass it my string. This guy will start a count off at 0 and just start walking through contiguous memory until it finally hits a \0, which is our string termination character. Each time through, as long as we don't see one of those, it'll add 1 to our count. There must be one more real character in this string. This is going to be our string count, not the length of it. Return count, this is what will print out. All right, so now depending on the vintage of the C compiler, I may or may not get an error right now. And that error has to do with, I am calling a function before that function technically exists. I know we're out of time. Let me just finish this in this 1 second. Go ahead and run it. Yeah, it's a, notice it does say implicit declaration of this function. It figured it out, though. It did what's called a 2-pass compiler. It made 1 pass and got figured out that this guy will exist. The old school C version of this is you should prototype your methods at the top there. So I can prototype it like that, kind of promising this dude will exist, and then actually write it later on. Nothing says I couldn't have written it up here, but sometimes you end up having a chicken or the egg problem, where you have one function that relies on another one, which relies on the one before it, and then you can't get it written. But in any case, we saw that I'm able to count the number of characters in a string, taking advantage of that knowledge that old style C strings are terminated with that \0. Make sense? All right, but the good news for us is we're going to be using new style strings that do a lot of that stuff for us. But we're just trying to really scare the crap out of us with the C++ stuff for a little bit. Questions, comments, concerns, bribes? All right, so you have that paper due on Wednesday, no class on Monday. We'll come back on Wednesday. I'll do a little bit more here, and then we're going to start talking about linked list. We'll talk about structs, then we'll talk about linked lists. Cool. All right, I'll see everybody next week.